Good evening, everyone. Good evening, everyone. This is problem solving session 6 for the NPTEL course CFD by Professor Sreenivas Jayanti. The problem solving session is conducted by Anchor Kartiga. So, as far as this course is concerned, we have seen few topics that were covered in previous weeks and solved problems accordingly. So we have seen, for example, the calculation of flow in a rectangular duct, calculation of flow in a triangular duct, and also the derivation of governing equation and equations for incompressible flow and boundary conditions. And also last week we specifically have seen about finite difference approaches, and this week it is mainly about consistency, stability, and convergence. We see how these can be determined in a problem and how what are all the problems that can be asked from these. So basically this week's focus is mainly about consistency, stability, and convergence. If at any point of time you do not understand, please feel free to stop and ask questions. Now we'll move on to the problems. For this week, for a change, we are solving practice problems first, followed by the assignment problems. So this is question A. In question A, it is asked that wiggles or stable spatial oscillations in regions of large gradients are an indication of what type of numerical error. So basically, what are all the numerical errors that we know? That is, we know round of errors, truncation errors, and discretization error, diffusive error, dispersive error, and so on. So wiggles are basically where there are more oscillations or various changes that is occurring in the system. For example, we'll take this a system. Consider this step down pulse. For example, if for this solution we are getting a somewhat solution like this is known as diffusive error. And the if instead of this we are getting solution like this is known as dispersive error. So what do you understand from this basically? Basically, it is if there is some deviation from the desired solution because of that the solution diffuses or changes dynamically, that is known as diffusive error. Whereas if there are more oscillations, we call them dispersive error. So this is the difference between dispersive error and diffusive error. So we will see what is the questions that is asked. I mean, what are the options that are given. So it is like first one is diffusive error, second one is dispersive error, third one is truncation error. So from this we know that if wiggles are there, it is dispersive error. So we will see that option 1 it is only diffusive error, option 2 it is dispersive error, option 3 it is diffusive as well as dispersive error, whereas option 4 it is diffusive, dispersive and truncation error. But we know the answer is dispersive error. So the answer is option 2, that is dispersive error. Answer 2 is the right answer. Now we'll move on to question B. In question B, it is asked that one Newman stability analysis is restricted to. Uh, we'll see the options. It is linear initial value problems, periodic boundary conditions, and linear boundary value problems. When we are speaking about von Neumann analysis, what does it mean? It is an approach where we are studying about the or arriving at the stability criteria. Mainly in numerical analysis, von Neumann stability analysis is a procedure used to check the stability of finite difference schemes as applied to partial differential equations. So basically here we are dealing with a procedure where we are checking the stability of the finite difference schemes when we are applying to linear partial differential equations. Uh, so here we are consider a system like we are taking if what is numerical error uh, when there is for example, consider the numerical error to be n, and we have the direct solution. uh, Okay, we'll keep it like this. We'll have the direct solution as D and some error as E and numerical solution as N. What would the numerical solution be? Numerical solution would be direct solution D with the error included. If D plus E becomes the direct solution plus the error, that gives the numerical solution. Basically, this is criteria is used to study the stability of a system. So von Neumann stability analysis is restricted to, mainly it is used for linear initial value problems and periodic boundary conditions. Only when these two criteria are there, we can use von Neumann stability analysis. In other cases, it cannot be used. So basically, von Neumann stability analysis is restricted to first one, linear initial value problems and periodic boundary conditions. 1 and 2 are the right answer. Option 3 is wrong. Linear boundary value problems is not applicable. So 1 and 2 is the right answer. We will see the options that are given. It is 1 and 2 or 2 and 3. Periodic boundary conditions and linear boundary value problems. Linear initial value problems. 1, 2 and 3, all the 3. No, the answer to this is option 1, where it is linear initial value problems together with the periodic boundary conditions. Now we will move on to question C. Okay, the answer to this is 1 and 2, that is option 1. We'll move on to question C. In question C, it is given which of the following does not affect the stability of a hyperbolic problem. Which of the following does not affect the stability of a hyperbolic problem? It is, the first one is mesh spacing delta x, second is velocity, third is viscosity, fourth is time step delta t. So in previous week session, we saw how hyperbolic, parabolic and elliptic problems solutions are approached for these problems in a different manner in terms of usage of boundary conditions and all. So basically, when we are dealing with hyperbolic problem, the thing is we would be marching if the solution at a specific point depends to a certain extent on the region of influence, which involves a smaller region. So thereby, here the thing to be noted is we need to know the mesh spacing and the time step dt together with how fast it is moving, that is the velocity. So basically 1, 2 and 4 are affecting the stability of a hyperbolic problem. Mesh spacing, velocity and time step. Viscosity does not play a major role in this. But the question asked here is which of the following does not affect the stability of a hyperbolic problem? The answer is viscosity, because viscosity does not affect the stability of a hyperbolic problem. We'll see the options. It is 1 and 2, mesh spacing and velocity, or viscosity and time step delta t, or viscosity alone, or velocity alone. So we know the answer to this problem is viscosity. Viscosity does not affect the stability of the hyperbolic problem. We'll move on to question D. Okay, the answer is option 3. Okay, now we'll move on to question D. In question D, it is asked that stability is a problem of differential equation, difference equation and computer accuracy. Stability comes into picture when the solution is somewhat approaching a stable things. So when this is used for getting the numerical solution procedures, so basically it involves differential equations, difference equations, and also the computer accuracy. So stability is the problem of differential equation, that is true, difference equation, that is also true, and computer accuracy, that is also true. So basically the answer is all three. One, or difference equations, or computer accuracy, or 1, 2 and 3. So the answer to this problem is fourth one, 1, 2 and 3. Answer is 4. If wiggles appear in a numerical solution, then what can be done to eliminate them? So just recollect it that what we saw about wiggles. Wiggles are spatial oscillations, stable spatial oscillations. So what can be done to eliminate them? Since it is depending on the dispersive in nature, we can reduce the grid size to get the wiggles to reduce. So the answer options given are decrease time step, decrease grid spacing, and use more accurate scheme. So it is either a decrease time step or a decrease grid spacing or use more accurate scheme. So the answer is decrease grid spacing. 1 or 2 or 3. No, that is also false. Answer is decreasing grid spacing. So this is actually week 6 content. By mistake it is written as week 5. I hope the practice problems are all clear for everyone. Now we'll move on to assignment problems. Choose the correct answers from the options given below. Note that there are some questions with multiple correct answers. So this is the given system. There are some deviations. We'll see what the question is for this problem and we'll decide. Okay. The first question is the unsteady two-dimensional advection equation with no diffusion is given by. First one, it is dou f by dou t is equal to dou f by dou x, or second one, it is dou f by dou t plus dou u by dou x plus dou v by dou x is equal to 0, or third one, it is dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0, or fourth, it is dou f by dou t plus dou f by dou x is equal to dou square f by dou x square. So what is advection term? And what, for example, when we are dealing with one-dimensional scalar transport equation, we would be getting the equation as dou f by dou t plus dou f by dou x into some constant is equal to constant times dou square f by dou x square. That is the one-dimensional scalar transport equation, which includes the terms advection as well as diffusion. So what does this advection do? The property that is getting transferred because of the movement of the fluid, that is advection. So basically it is like the property is varying with respect to position. Answer to this is this one. What is diffusion? Diffusion term is given by dou square f by dou x square. That is the RHS term in the one-dimensional scalar transport equation. It is the movement of molecules at molecular level. Okay. Now we just see how we have arrived at this term. Answer to this question is option 3. Dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. So basically the one-dimensional scalar transport equation is given by dou f by dou t plus dou f by dou x is equal to a dou square f by dou x square. This term is the advection term. This term is the diffusion term. For the same thing, when we are extending it to two-dimensional, okay, before two-dimensional, let us ignore the diffusion term. So the RHS term becomes 0. So then it would be dou f by dou t plus u into dou f by dou x is equal to 0. When we are extending it to 2D equation, what would it happen? Dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. So the answer to this question is option 3. Dou f by dou t plus dou f by dou x plus dou f by dou y is equal to 0. So I hope this is clear. The next one is a problem similar to this one. So I want you people to solve this and before coming into the solution part. So the question is, unsteady one-dimensional diffusion equation is given by, which is the equation for a is greater than 0. The first equation is dou f by dou t plus a into dou square f by dou x square. Second one is dou f by dou t minus a into dou square f by dou y square. Third one is dou f by dou t is equal to a into dou square f by dou x square. Just find out which one of the options are right. The option combinations are 1 is only 1, whereas in 2 it is 1 and 2, 3 it is 1 and 3, 4 it is 2 and 3. Just work it out and let me know the answers. So yeah, when diffusion equation is coming into picture, the RHS term dou square f by dou x square into constant remains the same. The diffusion advection term disappears over here. So basically it is dou f by dou t plus or equal to a into dou square f by dou x square, because a is greater than 0. So the thing is, this is not correct, because this symbol over here is plus, whereas it should have been negative, whereas this one is right, minus a dou square f by dou y square is equal to 0, whereas third one is also right, dou f by dou t is equal to dou square f by dou x square into e. So options 2 and 3 are the right answer. Fourth one is option 2 and option 3. I hope this is clear. We'll just see how it was framed. The one-dimensional diffusion equation is given by this term, dou f by dou t plus dou f by dou x is equal to a dou square f by dou x square, where dou f by dou x is an advective term and dou square f by dou x square is an diffusive term, and unsteady one-dimensional diffusion equation, therefore this term becomes 0 and this would remain, and when we take it to this one it remains negative. So options 3 and 2 and 3 are the right one, which is given by fourth. So the answer to this is 4. Now we'll move on to question 3. Which of the following is true about Courant number? Courant number is a condition on the stability of a numerical scheme. High value of a Courant number is desirable for consistency. Courant number does not arise for elliptic problems. Options are 1 or 1 and 2, 1 and 3, 1, 2 and 3. So guys, please figure out which is the right answer and why do you think so? or just take a piece of paper and write it over there. Whichever it is fine. So basically, what is Quran number? We'll go step by step. What is Quran number? Quran number is generally used for stability analysis or to find out the stability of the numerical scheme. Basically, it is a condition. It gives some condition. Whereas if the system of equation obeys that condition, uh, the system can be stable. Otherwise, instability would occur. So the Quran number is a condition on the stability of a numerical scheme. This is true. Second one, it is high value of a Quran number is desirable for consistency. No, it is not always that high value of a Quran number would give a good solution. No, a proper Quran number in the proper range with proper condition is required for consistency, not the higher value. So the second one is wrong. Second statement is wrong. Third one, it is Quran number condition does not arise for elliptic problems. It is true. Can anyone recollect what we saw about elliptic problems in the boundary condition thing? Okay, it was like a point is situated where we can use points from anything and we should solve the system simultaneously to get the solution, and therefore uh, it is, since in elliptic equation time marching is not possible, Quran number condition does not arise for this problem. So we are saying options 1 and 3 are right, and it is option 3. That is, third one is the correct answer, which gives first and third statement to be true. So what is Quran number? Quran number, how much information travels across a computational grid in unit time? It depends on dt and dx. So consider a system where we have a rod where the temperature at one end of the rod is very high and the temperature at the other end is nominal, room temperature. So the temperature would be decreasing from the one end to the other. Where the temperature is higher at one end, from there it would be decreasing. Just a minute. So yeah, Quran, we are taking a rod where there is one end is at higher temperature, other end is at a lower temperature or room temperature. So when we are grid sizing it, if we are making a very larger sized grid, imagine the solution would not be correct, right? Because one end it is at high temperature, other end it is at lower temperature, the temperature profile would not be going smooth. There would be a drastic change in it. Whereas if we take a very smaller grid size, we can make the profile to be correct. That is what happens, or this is what is decided by Quran number, like how much information or how much temperature it can be traveled across a computational grid over a unit time. Therefore, it depends on dt, that is unit time, as well as the dx, grid size. Basically, the first one is a true statement. Current number is the condition on stability of a numerical scheme. Whereas current number condition does not arise for elliptic problems. How are we supposed to say that? Elliptic equations, it is given by del square u is equal to 0. So basically dou square u by dou x square plus dou square u by dou y square is equal to 0. This is a form of elliptic equation. We can see that it is not depending on time matching. So we are not using time matching technique. Therefore, we are solving the equation simultaneously. If you remember in the previous case, it was a single thing where the point is dependent on all the other things. Therefore, we should solve the system simultaneously to get the solution. Therefore, since it is time matching is not happening, we need not use the Quran number criteria. So the answer to this is first and third. Third one is the option. Answer is option 3. Now we'll move on to question 4. In question 4, it is given which of the statements is correct about the discretization of one-dimensional unsteady diffusion equation. Option 1, it is Quran number limit does not apply. Option 2, it is consistent and unconditionally stable schemes can be developed. Option 3, it is FTCS scheme is unconditionally stable. What is here on reading this one question itself, there are so many questions that can be framed to analyze our understanding of the subject. So we'll see like which of the following statements is correct about the discretization of one-dimensional unsteady diffusion equation. Here we know discretization technique. We know like we can use various techniques to divide them into smaller cells so that we can pass the information across the smaller cells to reach or identify the larger transports. And one-dimensional unsteady diffusion equation we know, right? It is dou f by dou t is equal to dou square f by dou x square. That is one-dimensional unsteady and diffusion equation. So in one statement itself, there are various concepts involved. The first one is which of the following statements is correct? Quran number limit does not apply. Consistent and unconditionally stable schemes can be developed. FTCS scheme is unconditionally stable. So on looking at this, we can eliminate one option, that is Quran number limit does not apply. This is not true. We cannot say this. Whereas these two statements we need to check the identity. So basically since first one is wrong, 1, 1 and 1. Basically the answer to this question is option 4. 2 and 3 are the right answers. So we'll see how that is. Unsteady one-dimensional diffusion equation is given by dou f by dou t is equal to dou square f by dou x square. When we take this into the left hand side, we get dou f by dou t minus a dou square f by dou x square is equal to 0. We are using forward time central space. FTCS is forward in time, central in space, explicit scheme. So what is this? How are we getting this? We can just put it over here. For this equation, we would be getting it as F Fi n plus 1 Fi n plus 1 minus Fi n divided by delta t is equal to, we'll be getting a different thing, but it would be Fi at, since we are dealing with Fi, it would be Fi plus 1 at n minus 2 Fi n, this would be, again we would be getting fi minus 1 at n divided by delta x square. So this is the forward in time, central in space, explicit scheme. We should be noting it properly that it is an explicit scheme, not an implicit one. Implicit means we would not be using n over here, rather we would be using n plus 1. Therefore, it is very much to be noted over here. And then again we will put everything in a similar unit so it would not be confusing. If we rewrite this so that fin goes into singles, fin plus 1 alone remains in the left hand side and all other terms are going in this thing, we would be having a constant and we would be using it to define sigma, where sigma is a into delta t by delta x square. This sigma is should be less than or equal to 0.5 for in the forward time central space explicit scheme. This is explicit scheme to get the stability. So basically what it is meaning is it is conditionally stable. So it is not unconditionally stable, whereas it is conditionally stable. So the last before statement, FTCS is unconditionally stable is also wrong. It is conditionally stable. And it is given that implicit scheme okay, I'm sorry to say this, I missed out a point over here. Quran number limit does not apply. The statement, there is no limit, right? We are having only a criteria, so the statement is also correct. Quran number limit does not apply, and it is unconditionally stable. Sorry, it is conditionally stable, not unconditionally unstable. And consistent and unconditional stable schemes can be developed. The example for that is Crank-Nicholson scheme. It is unconditionally stable. Unconditionally stable and consistent schemes can also be developed. So that the point to be noted here is that it is Quran number limit does not apply, and consistent and unconditionally stable schemes can be developed. So the answer to this question is 1 and 2. Answer is option 2. Sorry, answer is option 2. It is Quran number limit does not apply, and also the unconditionally stable scheme and consistent schemes can be developed. So okay, now we'll move on to question 5. In question 5, it is shown that exact solutions and the computed solutions as a function of x at a particular time instant. The difference between the two is attributed to. So this is the figure 1 where exact solution, that is the solution shown by the dark line, that is dark black line, and the computer line, the dotted line, is a function of x at a particular time instant. So there is obviously a difference between the exact solution and the computed solution. The difference between the two is because of truncation error in space or truncation error in time, or both. So, or neither. It is seen that there is a deviation or the downward falling curve occurs below, before the solid line, for the dotted line. The downward falling thing is happening well before for this dotted line than the solid line. So there is truncation error in time. And also we can see that there is a certain deviation between this dotted line and the solid line. So there is truncation error in space also. So the answer to this is truncation error in space as well as truncation error in time. I hope this is clear. Now we'll move on to question 6. For one-dimensional wave equation, which of the following are true for the FTFS explicit scheme? So it is first order accuracy, inconsistency and unconditional stability. Basically, FTFS, that is forward time forward in space scheme, is given by for what? Basically we are dealing with a wave equation where it is dou u by dou t plus a into dou u by dou x is equal to 0. For that we should identify what are all the statements that were given previously are right. When we are discretizing it, we would be getting forward time, right? So it is uin plus 1 minus of uin by delta t plus a into ui plus 1 at n minus ui at n divided by delta x is equal to 0 basically. That is what we would be getting, right? But when we are denoting this equation, we are writing it as minus dou u by dou t plus a into dou u by dou x at I at power n. What are all the terms that we are neglecting? Del t by 2 uh, into dou square u by dou t square at I and n plus del x by 2 a into dou square u by dou x square at I and n. So basically these are first order in space and first order in time because it is of order delta t and delta x. First order in space and first order in time. And FTFS, when we are limiting the delta t and delta x, consider we are making it to be 0. Or they are very small, that we are considering it as 0. Delta t is equal to 0 and delta x is equal to 0. All the terms in the right hand side vanishes. So this would be equal to this. So the scheme is consistent. When the thing to be noted is it is true when it is of limiting case at very small delta t and delta x tending to 0. So what are the options? First order accuracy, that was right. We saw them to be first order in space and time. And it was consistent. It was not inconsistent. And unconditional stability. That was also not right. So the answer to this problem is option 1, that is first order accuracy is the right answer. Now we'll move on to question 6. Oh sorry. We'll move on to question 7. Before that we'll take a small break and we'll start the session back in 5 minutes. So yeah, we'll resume the session now. Sorry for a long break. Which of the following schemes may give assurance of convergence for the unsteady advection equation? It is FTBS explicit, FTFS implicit, CTCS implicit. So the question is asked for unsteady advection equation. So we will see which one of the following is giving assurance of convergence. So uh, it is like 1, 1 and 2, 1 and 3, or 1, 2 and 3. Basically it is the advection equation is given by dou u by dou x plus a into dou u by dou x is equal to 0. If we are going for forward in time and backward in space, we would be getting this equation. Whereas how these equations are formed is that we saw previously in some problem, right, for advection equation. Yeah, this one. Okay, this is for diffusion equation, but still it is fine. We'll copy and put it over there and we'll discuss when we are discussing question 7. New slide. It's question 7. It is advection equation is given by dou f. This one is the advection equation. So when we are dealing with question 7, it is dou f by dou t plus dou f by dou x a times dou f by dou x is equal to 0, because it is not advection, it is it is advection and not diffusion. When we are dealing with forward time and central space, we would be getting it as fi n plus 1 minus fi n by delta t is equal to a into the okay, here it would be plus a into f I plus 1 at n minus it would be f I minus 1 at n divided by 2 times of delta x. It is not delta x square. This is forward time and central space. And if it is forward time and backward in space, what would we get? We'll forward time, forward space, and forward time, backward space. What would be happening? It is fi plus 1 minus n. Here it would be fin. Similarly, it would be fin at minus fi minus 1 n by delta x, not 2 delta x. So this would be the difference between forward time central space and forward time backward space and forward time forward space. And one more thing that was asked is central time and central space. All these are explicit scheme. That's what we should be noting over here. Okay, cancel. It is central time, central space. Okay, it's okay. Explicit scheme. Basically it would be this one, similar to this. It would not be n and the other it would be n minus 1, and this term would be there. In all these it would be equal to 0. That we have forgot to put equal to 0. So these are all the terms. So basically if we are using this scheme, okay, what was asked is convergence, giving assurance for convergence. So basically these were the things that we were putting, and we can see that unsteady advection equation is given by this, where okay, we have already mentioned this. Okay, same as that problem, but rather we should be using it as f than u and constant as a. so that it would be remaining uniform. That's why I'm changing, and no other reasons. uh, it should be A, it would be dou f by dou x, and similarly it would be f, and it is f again, it is f. Again we should go and change here. We can see, right, it is yeah, one more thing that we should be focusing on is implicit versus explicit schemes. Can anyone tell the difference between implicit as well as explicit schemes? um, and because the first slide whatever we have written was for explicit, not for implicit, but in the question some things were asked for implicit as well. For example, ftbs explicit that we have written, ftf is implicit, and ctcs implicit. So what should we be doing is that ft what was that, ftfs implicit, ftfs. So again we should be copying it, and what difference we will make, we will see. It is implicit. Oh, the difference between explicit and implicit schemes come in the form of this, where if we use nth time step it is explicit, and if we use n plus 1th time step it is implicit. So ftf is implicit scheme. For to become implicit we should change the time step to n plus 1. Similarly for ctcs we have written it you for explicit. To get it for done for implicit, we should be changing it to n plus 1th time step than the nth time step. So it is n plus 1. I hope this is clear. So in a similar fashion, if you are using this, we can assure that all the three would be giving convergence under some conditions or so. So they would be giving the assurance for convergence. So FTBS explicit, FTFS implicit, CTCS implicit, all three are ready to give the convergence for the unsteady advection equation. Now we'll move on to question 8. I hope this is clear. Which of the following schemes is only conditionally stable for the unsteady diffusion equation? FTCS explicit, Crank-Nicolson scheme, and Dufort-Frankel scheme. Either FTCS explicit or Crank-Nicolson scheme, or Dufort-Frankel and FTCS, or FTCS and Crank-Nicolson scheme. Which of the following schemes is only conditionally stable? The question is about conditional stability for unsteady diffusion equation. So before moving on to that, we should know the diffusion equation. So okay, let us go by this way. We'll write the equation and we'll solve them step by step. Where was the diffusion equation, by the way? Yeah, it is here. New slide. It is question 8. So the diffusion equation, it is given by this term becomes 0 for diffusion equation. That previous one was one dimensional scalar transport equation. For diffusion term, that advection term becomes 0 and this term remains. So what are all the things that are given? FTCS explicit, Crank-Nicolson, Dufort-Frankel scheme. So basically, forward time central space, right? FTCS. For FTCS, it would be forward in time, right? So it would be F I n plus 1. It would be F I n plus 1. It would be F I. It would be F I n plus 1 forward time. So it would be minus uh, again this one, whereas now it is n, divided by delta t would come. Where was the delta t, delta t, delta t? Okay, we'll take this and we'll put it over here. Delta t is equal to a times dou square f by dou x square. So it would be forward times central space. So it is time step would remain constant because since it is explicit scheme, it is fi plus 1 at nth time step minus 2 fin at nth time step plus fi minus 1 n. Divided by delta x square delta x square. This is forward time central space. Now Crank-Nicolson scheme. In Crank-Nicolson scheme, what we are doing is the same equation would remain the same, but we are going in an this is explicit approach. Thing to be noted is it is explicit approach. Whereas in Crank-Nicolson scheme, this is we are calculating at n plus 1, sorry, nth time step, as well as one more calculation goes for the n plus 1th time step, and then we take the average of these two and get the things done. So it is 1 nth time step plus taking the average of n plus 1th time step together with the nth time step. Putting together all these, we will get the Crank-Nicolson scheme. Another thing is Dufort-Frankel. Okay, sorry. Dufort-Frankel. This also the thing remains same, but we are fi n is changed into fi n minus 1 is equal to fi n minus 1. We'll put like n plus 1 plus n minus 1 divided by 2. We are taking the average. Divided by 2. This is for Dufort-Frankel scheme. This is what we are doing for Dufort-Frankel scheme. If we are replacing in such a way, this would become as fi by 2. So it would be n minus 1 divided by 2 delta t, and here it would be 2 and 2 gets cancelled, fi n plus 1. Okay, fi, okay, here all are like nth time step. It is nth time step. Again this is nth time step. Here I am like cutting down all these. So it would be 2 minus fi n plus 1 minus fi n minus 1. Yeah. This is Dufort-Frankel scheme. The Crank-Nichols, we can clearly see that forward time central space is first order in time and second order in space, whereas Crank-Nicholson and Dufort-Frankel are second order in both space and time. What the question asked was, which of the following is only conditionally stable for unsteady diffusion equation? So for this unsteady diffusion equation, which of the following is conditionally stable? uh, Conditionally stable. So basically this equation and that equation are basically the same. We have just written in R, so we'll just delete this. So forward time central space explicit is conditionally stable, whereas for Crank-Nicolson is unconditionally stable, Dufort-Frankel is unconditionally unstable for this diffusion equation. So the answer is forward time central space is conditionally stable. Crank-Nicolson is unconditionally stable, Dufort-Frankel is unconditionally unstable. I hope this question 8 is clear. Now we'll move on to question 9. Which of the following schemes is second order accurate in both time and space for the unsteady equation? Forward time central space explicit, Crank-Nicolson scheme and Dufort-Frankel scheme. It is observed that it was same as the previous question, where it is asked that second order accurate in both time and space. We already saw that forward time central space is explicit is first order in time, whereas second order in time, Crank-Nicolson and Dufort are second order in time. Space, all three are on second order in space. So the answer is 2 and 3. We can say that Crank-Nicolson scheme and Dufort-Frankel schemes are both second order accurate in time as well as in space. So we'll just delete this. Okay, now we'll move on to question 10. In question 10, it is asked that for the one-dimensional scalar transport equation with no source term, which of the following will give oscillation-free stable solution with second order accuracy in both time and space? Forward time, backward space and central space explicit, forward time, central space explicit, central time, central space and central space implicit. For the following one-dimensional transport equation with no source term, which of the following will give oscillation-free solution with second order accuracy in both time and space? So the answer is none of the above. How was that we identified as what is one-dimensional scalar transport equation? It is dou phi by dou t plus u into dou phi by dou x is equal to some constant time dou square phi by dou x square. For forward time central space scheme, we get it as phi I n plus 1 minus phi I n by delta t plus u into phi I plus 1 at n minus phi I minus 1 at n by 2 delta x, because this is central scheme, is equal to that constant times phi I plus 1 n minus 2 phi I n plus phi I minus 1 n by delta x square. This is forward in time and central in space. Since this is not accurate enough, we are going for the upwinding scheme where the advection term is reduced in the accuracy. So it becomes backward in space so that the accuracy is reduced. That is known as forward time, backward space and central space. And if it is central space only, it is forward time, central space explicit. In both of these, they are first order in time. They are not second order in time. Whereas central time and central time, central space and central space gives implicit. It is accurate in second order accuracy it is having, but it is not stable. So it is not giving oscillation free stable solution, because we could see that for previous FTCS CS itself it was not giving solution, therefore only upwinding was happening. So the answer to this problem is none of the above. So None of the above, that is option 4 is the right answer. Option 4. Okay. Now let us have a very small session where it is an interesting session. So before that, every one of you, if you want to take a break, just take for 5 minutes and come back fast. So yeah, we'll resume our session. Basically, what is happening? What will is the point is here is um, okay. We have seen here 7 questions are presented for you. Just small conceptual questions. So I'll read out the questions. Please try to answer the questions in a piece of paper or so. And then at the end of the 7 questions, we'll discuss the answers. Answers are not provided in between. So these are just not problem solving type, just a conceptual questions to test whether we have understood or not. Okay. Question 1. Which of these properties is not included in Lax equivalence theorem? Option 1, stability. Option 2, it is boundedness. Option 3, it is consistency. Option 4, it is convergence. Okay. I'll just repeat the question and give you guys a minute or two, and then we'll discuss at the end. Okay. Which of these properties is not included in the Lax in equivalence theorem? Stability, boundedness, consistency, convergence. A solution is ideal. Okay. Okay, you guys just write. We'll just solve it. Think for a minute and then write. Or if you're sure, you can write immediately. No issues. Which of these properties is not included in the Lax equivalence theorem? Stability, boundedness, consistency, convergence. Lax equivalence theorem, I hope everyone remembers. We also saw a glimpse of it in the last session. Okay, moving on to question 2. It is, a solution is really converged if the results match with the exact solution, the results for 2 consecutive iterations are the same, the results for 2 schemes are the same, the results for different boundary conditions are the same. So, a solution is ideally converged if the results match with the exact solution, the results for 2 consecutive iterations are the same, the results for 2 schemes are the same, the results for different boundary conditions are the same. Okay, now we'll move on to question 3. In real, how is convergence defined? Variations are accepted when the variation is less than the result, when the variation falls below a certain acceptable range, when the variation is the same as the result. I repeat, in real, how is convergence defined? Variations are accepted when the variation is less than the result, when the variation falls below a certain acceptable range, when the variation is the same as the result. Question 4. Which of these statements is wrong? Convergence is applicable for iteration processes. Convergence is affected by accuracy and efficiency. Converged solutions do not vary much with further iterations. Converged solutions are exact. Which of these statements is wrong? Convergence is applicable for iteration processes. Convergence is affected by accuracy and efficiency. Converged solutions do not vary much with further iterations. Converged solutions are exact. Okay. Which of these is used to analyze the stability of a system? Option A, Nusselt number. Option B, Courant number. Option C, Peclet number. Option D, von Neumann's method. Which of these is used to analyze the stability of a system? Nusselt number, Courant number, Peclet number, von Neumann's method. Okay. Which of these iterative processes is unstable? Uh, eta n is the error in the nth iteration. So option A is eta n plus 1 by eta n is equal to 0.5. Eta n plus eta n is equal to 0.75. eta n plus 1 eta n is equal to 1.25, eta n plus 1 by eta n is equal to 1. Which of these iterative processes is unstable? Where eta n is the error in the nth iteration. So eta n plus 1 by eta n is equal to 0.5, eta n plus 1 by eta n is equal to 0.75, eta n plus 1 by eta n is equal to 1.25, eta n plus 1 by eta n is equal to 1. In one human analysis, the solution is expanded using Lorentz series, Maclaurin series, Taylor series and Fourier series. In one human analysis, the solution is expanded using Lorentz series, Maclaurin series, Taylor series and Fourier series. So these are the 7 questions. If you have written, we'll just see the solution to this. And so these are the solutions. Now we'll go back to the questions and discuss once again what the answers are. Okay. Which of these in question 1 it is asked that which of these properties is not included in the Lax equivalence theorem. So can anyone remember what we saw about Lax equivalence theorem in the last session? Or in general, like in the lecture series also, sir was teaching about Lax equivalence theorem. So if any one of you remember that, you can unmute yourself and say. Okay. What it was saying is that for any system, stability and consistency is a necessary condition for convergence of the solution. Basically, what Lax equivalence theorem states is that stability and consistency are the required criteria for the well-posed time-dependent linear partial differential equation to be convergent. For example, if the solution of the partial differential equation if for a well-posed linear partial differential equation to be convergent, stability and consistency is the criteria. So what are all the included things in the Lax equivalence theorem is that stability is included, consistency is included, convergence is also included, whereas boundedness is not included. So the answer to this problem is option B, boundedness. Yeah, now we'll move on to question 2. A solution is ideally converged if the results match with the exact solution The results for two consecutive iterations are the same. The results for two schemes are the same. The results for different boundary conditions are the same. Our solution is ideally converged if what happens? The answer to this is, when do we say convergent? If two consecutive iterations are the same. So answer to this problem is also option B. When two schemes are same, we don't call it converged solution, and most cases it won't be the same. Results match with the exact solution, that also it would not be occurring. There would be some mismatch between the exact solution and the results that we are getting, because we are having some round of errors or truncation errors and so on. Results for different boundary conditions are the same. It is not practically possible, and also not really, and we do not mean convergent in that such case. We mean convergent if the results for two consecutive iterations are the same. In real, how is convergence defined? Variations are accepted when the variation is less than the result, when the variation falls below a certain acceptable range, when the variation is same as the result. Variation is like difference between the exact solution and the solution that we are getting. Variations are accepted, it doesn't make sense. Like there should be some value below which the variation would be accepted. Variation is less than the result, it should not be less than the result, it should be less than some tolerance value. Variation falls below a certain acceptable range, this is the answer. When the variation is the same as the result, that also won't be possible. So answer to this question is option C, when the variation falls below a certain acceptable range. We'll move on to question 4. Which of these statements is wrong? Convergence is applicable for iteration processes. Convergence is affected by accuracy and efficiency. Converged solutions do not vary much with further iterations. Converged solutions are exact. Convergence is applicable for iteration processes. It is true, when we are iterating, we expect that solution between the present value and the previous value to be somewhat similar. So it is applicable for iteration processes, true. It is affected by accuracy and efficiency, it is also true. The order of accuracy, everything plays a matter and plays a prominent role. So convergence is affected by accuracy and efficiency. Converged solutions do not vary much with further iterations. This is also true. When if the solution is converged, there is no need for it to vary further, right? So the converged solutions do not vary very much with further iterations. Converged solutions are exact. This is false. Converged solutions are not exact. It is not about the matching. Some variations would still be there. Okay, we'll move on to question 5. Which of these is used to analyze the stability of a system? Nusselt number, Courant number, Peclet number, von Neumann's method. The method that is used to analyze the stability is known as von Neumann's method, where we use the technique like adding numerical solution would be direct solution plus the error. When we are adding it, we get the numerical solution, and by using the Fourier series transformation, we put it in the original equation and arrive at the stability criteria. Like Courant number should be this, Peclet number should be these. These are all the product of the von Neumann stability analysis criteria. Major thing that is used to analyze the stability of a system is the von Neumann's stability analysis method. We'll move on to question 6. In question 6, which of these iterative processes is unstable? Instability is where the error keeps on reducing. Unstability is the exact opposite, where the error keeps on growing. Epsilon n is the error in the nth iteration, and epsilon n plus 1 is the error in the n plus 1th iteration. So basically, if the error between the next step, the present step and the past step should be low, right? Because in the present step, the error should be lower than in the past. So the 1 and below values, lesser than 1 values, are stable. If it is epsilon n plus 1 by epsilon n is equal to 0.5, epsilon n plus 1 is equal to 0.5 times the epsilon n. That is, the error is half of that in the last step. The present error is half of that in the last step. So it is acceptable. Whereas in option 3 it is given that epsilon n plus 1 by epsilon n is equal to 1.25. That is false. It should not keep on growing, it should rather keep on decreasing. Therefore, option 3 gives rise to unstable solutions. In von Neumann analysis, the solution is expanded using Lorentz series, Maclaurin series, Taylor series, and Fourier series. This one we discussed previously also in how we do von Neumann analysis. There we use numerical error is equal to how it can be arrived at from the direct solution, numerical solution, how it is related to the direct solution, and putting it in the discretized equation as well as using the Fourier series, we get the analysis criteria. So the answer to this is Fourier series. So these are all the answers for the last 7 questions. They are just simple conceptual questions I thought would determine our level of understanding the concepts. So that's all for today, and I thank you and everyone for attending today's session. So please feel free to ask any questions if you have any. I'll be happy to take on the questions. Okay. I'll wait 2 more minutes for taking up any questions. If not, I'll just give a quick recap of today's session and we'll close the session. So yeah, since there is no questions, we'll just close the session by giving a quick recap. In today's session, the main focus was mostly on convergence, consistency, and stability, and we saw the problems of different types of error like diffusive error, dispersive error, and truncation error, and how dispersive error is the oscillations. And also we saw the von Neumann stability analysis, which is used for linear initial value problems as well as the periodic boundary conditions, and which uses Fourier series to analyze it. And there are few problems like how this what are all the properties affecting the stability of a problem, and what are all the properties that does not affect the stability in a hyperbolic problem, and what is stability like, and how to reduce the oscillations. By one of the ways by decreasing the time grid spacing. And it was like then it was followed by the one dimensional scalar transport equation with advection and diffusion terms, and extend with further extension to the 2D cases. And like Quran number, we also focused on Quran number, how it is arrived as a criteria from the von Neumann stability analysis, and how it denotes how much the information is traveling across the grid and across the time step. and few other concepts based on Quran number. And we focus mainly on the one-dimensional scalar transport equation with different schemes for discretization, like forward time, central space, and central time for central space with forward space or backward space. All these schemes were studied in the lecture with few questions to be answered, and also the implicit scheme and explicit scheme, where in explicit scheme we use the nth time step, and for implicit scheme we use the n plus 1th time step, and also truncation error and the order of accuracy, and for different schemes, and the convergence criteria for the different schemes. It can be analyzed by using the von Neumann stability analysis, and most probably we were focusing only on that. And another thing was, we also saw about Frank Nicholson scheme, where we took the average between n and n plus 1th time step, whereas in Dufort Frankel scheme we used nth time step to be an average between n minus 1 and n plus 1th time step. And also we saw like one dimensional scalar transport equation with no source term with advection and diffusion term, where we use the central scheme. For if we are using a central scheme and not obtaining the proper results, we use the upwinding to bring back it to backward spacing in the first order. So it was about second order accuracy in both time and space, and we saw few problems regarding conceptual understanding like Lax equivalence theorem and convergence mostly. So the following statements is wrong, like convergence, von Neumann stability analysis, and stability, instability, and so on. These were the answers to that, and I thank every one of you for attending this session. If there is no doubts or any concerns or queries, the session is over, so you people can leave. Thank you everyone. We'll meet next week in the same time, 6 to 8 p.m. And today's lecture is over. Thank you.